some people will say they, of course, understand everything about quantum field theory, but we don't understand it as the complete structure. To really understand superposition as a quantum, you have to be a quantum entity.
Professor Nikita Nekrasov unified previously disconnected fields: instanton moduli spaces, random partitions, integrable systems, and quantum strings. What was required was so novel that when he was presenting at conferences, other physicists couldn't tell if his results contradicted or confirmed theirs. His mentor, David Gross, advised him, "Keep your poker face." That gamble paid off. It turns out 4 dimensions aren't arbitrary. I'm Curt Jaimungal, and I interview researchers regarding their theories of reality with technical depth. Today we explore how non-commutative geometry cures quantum singularities, why understanding superposition requires becoming quantum yourself, and Nikita's speculative connection between R4's exotic smooth structures and the chemistry undergirding life itself. From falling asleep during Witten's seminal lecture to late-night residue calculations with Greg Moore, this is mathematical physics at its most human and revolutionary. Why don't we understand quantum field theory?
So it probably depends on who you ask. So some people will say they, of course, understand everything about quantum field theory. Practitioners who use it, they will tell you that they understand because they know how to use it, and they know how to do some calculations, which will then can be maybe compared to experiment. And more often than not, the comparison is favorable. So we don't, maybe as theoretical physicists with some kind of mathematical ambitions, we don't understand it as the complete structure built out of axioms, let's say.
So you want an axiomatic quantum field theory that reproduces all of the successes of the standard model?
Something which, we would like to have some basic principles, like maybe not axioms, but some basic principles from which we can build structure, from bottom to top, bottom up. We have many examples of what we think quantum field theory is. So many examples of quantum field theories, and there are many overlaps, but there are also missing kind of areas. We don't know whether gravity is part of quantum field theory or it's something else which requires a different approach. And so there are many questions like that. So there is, of course, a very practical approach which works with many theories which are involved in standard model, which you can just simulate them on a computer. Just do largest field theory.
Right.
There are various subtleties with that, because not all structures which we know there are in smooth fields, and like fields defined on smooth manifolds. Manifolds may have different structures, like spin structure. All those things are kind of hard to represent faithfully on a lattice, but with some room for error, people do that. But that looks still looks like a bypass, not the whole thing. And we know examples of quantum field theories which probably don't have lattice description.
Mm-hmm.
And so the work which we do, some of us do, which are actually trying to chip away at the unknown in connecting us to those theories by coming up with maybe mathematical conjectures which sort of follow from the fact that these theories exist, and then checking them maybe by more standard means, and then gaining more confidence that the reason for those conjectures to be there probably is valid.
Uh-huh. Now we're going to build up to gauge origami, but before we do, I want to get to another one of your constructions. So Dirac said to Feynman, infamously, "Do you have an equation?" And Feynman could have said to Dirac, "Well, do you have a diagram?" And now I'm thinking you could have chimed in and said, well, do any of you have a partition function?
Well, of course they had lots of partition functions.
Yes. But anyhow, you have one named after you. So let's get to that story. I believe this was around 2002 where you cracked the Seiberg-Witten instanton counting puzzle, which was when in the mid-1990s?
1994, yeah.
Right. And it was there where you devised the Nekrasov partition function. So tell us about what that partition function is and what it was like coming up with that solution. Was it a lightning bolt? Was it an incremental climb? What did that moment feel like?
Yeah, so this is a story which is a kind of worth a book because it's a story worth of many sleepless nights, but also
there's a book called The Count of Monte Cristo. So yours would be The Count of Instantons.
Right. Thank you for observing the analogy. Right. You have to dig an underground tunnel from some predicament you are to actually to get to the dry land. And some people say there is also vengeance involved, but in my story, no vengeance. It's all pure love. Just.
Are you sure?
Well, at least that's my inner work. So my inner work is to realize that all we do in science is joy. It's even though it feels like suffering along the way, but the goal is to recognize beauty and maybe add a little bit of beauty and use it later. Just because beautiful things are good to have around, and sometimes they're useful. So the story started, I don't know when it started actually, maybe started in 1992. Witten wrote a paper which was called Two-Dimensional Gauge Theories Revisited. And in that paper, he proposed to use a technique from rather abstract mathematics at the time called equivariant localization to compute the path integral. So it's a Feynman integral over trajectories or field configurations. An example of a rather simple but nevertheless interesting gauge theory, two-dimensional Yang-Mills theory. So our world is described to some approximation by four-dimensional Yang-Mills theory, quantum Yang-Mills theory. But if you imagine a world in which there is only one space dimension and one time dimension, then you could study the simplified version of Yang-Mills theory. And that was a theory which was actually solved by several tools. But the one tool which was kind of interesting was by Alexander Migdal, who actually first defined it using lattice approximation. And then he found out that it was an interesting theory in which you can define it on any kind of lattice. You can make the lattice finer or economical, so use as little number of edges as possible.
Yes.
Given the topology of spacetime, and the partition function will be the same. So it was an interesting theory which was almost topological. We would not call it now almost topological. It only dependent on the area of spacetime. So spacetime, here I'm using a little bit of a jargon. The theory is interesting when spacetime is not physical spacetime, when you have time and space, but what we sometimes call Euclidean spacetime. So it's a manifold in which the notion of a distance between points is similar to the notion of distance between points in space. So it's ordinary. There is ordinary Riemannian metric. How it is connected to the space-time, where the notion of distance involves events, and so some distances can have negative square, for example. That's a story which we can discuss, but it's let's not get there.
Okay.
Anyway, so Witten observed that this theory, the reason why Migdal was able to solve it and get a very interesting answer So Witten observed that it had to do with certain topological structures present in the finite dimensional space, which you can associate to any two-dimensional surface. We call them Riemann surface. So it's like a surface of a. Well, your audience knows probably what Riemann surfaces are. So Riemann surfaces have, if they are orientable, they have only one number which characterizes the topology, the number of handles. And so now Yang-Mills theory deals with connections, with the ways to transport things from one point to another over some in some bundle over the base space. And the lowest energy configurations, lowest action configurations in Yang-Mills theory are the connections which have zero curvature, which means that if you transport things around small loops, the result doesn't depend on which loop you choose, as long as the loops are small. But if the loops are not small, if they wind around handles, so they cannot be contracted to a point, then those transports can be non-trivial. This fact actually was observed in physics in the famous Aharonov-Bohm experiment. So it's a famous story which showed to the world and to physicists also that the connection, the vector potential, actually has a meaning, has a physical meaning, not just the curvature. Which, if you're familiar with Maxwell equations, you can write them only using the curvature, this field strength. And so for a while, people thought that the vector potential is not really meaningful because, first of all, it's not universally defined. You can make the so-called gauge transformation and change it. But the fact that they transport, especially the transport observed by quantum particle, depends on the path which can be non-contractible, it was a big deal. And so on the two-dimensional Riemann surface, because you have several handles, you can have those transports, and then they can have pretty much arbitrary values. And there is a space which parameterizes them, which is called the modular space of flat connections. These days, this space is, of course, very popular in the stories involving geometric Langlands program. But anyway, so if your connection, if your gauge theory is defined with compact gauge group, then it's some compact space, although with singularities, because you have symmetries and you divide by symmetries, and sometimes symmetries act not freely, so it's a singular space. But you can define its volume. It has a natural, it turns out it actually could be viewed as a phase space. It has a symplectic structure, which was actually found by, I guess, Atiyah and Bott in the early 80s. And so there is a natural number which you can associate to every Riemann surface, which is the volume of that modular space computed in the Liouville measure.
Right.
And so Witten computed this number by a very clever trick using localization applied to two-dimensional Yang-Mills theory. Got beautiful answers involving zeta functions. So some of us now call them Riemann-Witten zeta functions because for SU2 these are just Riemann zeta functions, but for other groups they kind of generalizations. So these are interesting objects. And anyway, so in 1992, I was just beginning my studies. I was very much impressed by the paper. In fact, my friend and later collaborator, Andrei Lossev, suggested I study that paper and present it at a seminar. So you know I come from Moscow, so I was attending some string theory seminars there. And the tradition there was that you study some paper, and this was the beginning of archive. So it was the first, maybe second year of archive. So the papers from the West started coming in not by spam prints in some diplomatic post, but as actual paper you can print out if you have a printer, which of course nobody had, but that was a second order problem. And so you study the paper and you present it to your friends and colleagues, and then they grill you for several hours, and then you understand you have to study more, and then you go back and you study more.
And at that point, you were an undergraduate?
I was undergraduate student at the time, so it was my probably third year after high school.
Right.
So, but I mean, I already knew what I wanted to do, so I was lucky to get interested in mathematical physics, in what I call mathematical physics, right early on, and so somehow I got into this group of people discussing whatever was interesting. So I was very much impressed with this paper, and I thought, okay, maybe one can use this localization to compute interesting things in other theories. And I remember we were discussing with my other friend and also collaborator later, Sasha Gorsky, and we asked ourselves, why couldn't we apply this supersymmetric technique to in quantum mechanics, so quantum integrable, especially quantum integrable systems. Later on, the spectrum was analyzed by Duncan Haldane, who got Nobel Prize for many, many things. And so the way the spectrum was organized is now called Haldane statistics. So these particles, because of this particular interaction, they kind of behave as neither bosons nor fermions, but something like in between. And so this coupling constant can be an interpolating parameter. Anyway, Gorsky and I found that this model of particles moving on a circle and repelling each other with the potential which is proportional to inverse square of the distance, chord distance, is actually a part of the two-dimensional Yang-Mills theory. So quantum mechanics is equivalent to two-dimensional theory. So it's one of the interesting examples of deceiving dimension. That's part of this. This is part of the structure which I mentioned when I say that we don't quite understand quantum field theory, because when we explain to engineers that quantum field theory is the continuous limit of something you define in the lattice, of course, an engineer will think that, well, the lattice is embedded into space-time of some dimensionality, so that's the dimensionality of the theory. But it turns out that you can define a theory in one number of dimensions, but then by looking at special observables, so by restricting the set of observables you're allowed to look at, you will not be able to distinguish it from the theory in the, let's say, lower dimensions, and vice versa. So we think we live in 3+1 dimensional space-time, but it might be just that we don't have access to observables which can probe, high dimensional space-time.
And eventually it's said that your work implies that particles live across multiple dimensions at once. Maybe particles is not the correct word here, though.
When I was talking about particles in the Calogero model, that was more of a just mental picture, like beads, like some small objects. So in particular, in this case, the way this relationship between quantum mechanics and field theory was working was that the role of those particles was played by the eigenvalues of the holonomy, so the transport of the two-dimensional gauge field around the circle of space. We found that those points in the circle behave so time continues to be the time. So those points in the circle behave as particles in Calogero-Sutherland model. The mathematicians call it Calogero-Moser-Sutherland model because Jürgen Moser, the Swiss mathematician, found a very neat way of explaining the integrability of that model, which we'll probably get to later.
Mm-hmm. So how does this relate to your partition function?
Not yet. So we are like 10 years before that.
Just a moment. Don't go anywhere. Hey, I see you inching away. Don't be like The Economy. Instead, read The Economist. I thought all The Economist was something that CEOs read to stay up to date on world trends. And that's true, but that's not only true. What I found more than useful for myself personally is their coverage of math, physics, philosophy, and AI, especially how something is perceived by other countries and how it may impact markets. For instance, The Economist had an interview with some of the people behind DeepSeek the week DeepSeek was launched. No one else had that. Another example is The Economist has this fantastic article on the recent dark energy data, which surpasses even Scientific American's coverage, in my opinion. They also have the chart of everything. It's like the chart version of this channel. It's something which is a pleasure to scroll through and learn from. Links to all of these will be in the description, of course. Now, The Economist's commitment to rigorous journalism means that you get a clear picture of the world's most significant developments. I am personally interested in the more scientific ones, like this one on extending life via mitochondrial transplants, which creates actually a new field of medicine, something that would make Michael Levin proud. The Economist also covers culture, finance and economics, business, international affairs, Britain, Europe, the Middle East, Africa, China, Asia, the Americas, and of course, the USA. Whether it's the latest in scientific innovation or the shifting landscape of global politics, The Economist provides comprehensive coverage, and it goes far beyond just headlines. Look, if you're passionate about expanding your knowledge and gaining a new understanding, a deeper one, of the forces that shape our world, then I highly recommend subscribing to The Economist. I subscribe to them, and it's an investment into your intellectual growth. It's one that you won't regret. As a listener of this podcast, you'll get a special 20% off discount. Now you can enjoy The Economist and all it has to offer for less. Head over to their website, www.economist.com/toe, TOE, to get started. Thanks for tuning in, and now let's get back to the exploration of the mysteries of our universe. Again, that's economist.com/toe.
So 2 years later, okay, so let's just keep it. So let's just remember that there is some relation between quantum many-body systems and gauge theories with some supersymmetry.
Okay.
And that in gauge theory, certain things can be calculated exactly if you can recognize some symmetry and can use the mathematical tool of equivariant localization.
Got it.
So 2 years later, it was 1994, and I was traveling, one can say backpacking through Europe, and I found myself in Paris when it just happened, the International Congress of Mathematical Physics took place. And so there was an interesting talk. There were 2 talks by Witten there, who presented his work with Seiberg on Seiberg-Witten solution of n equals 2 gauge theory, and on his work with Kumunwafa on the strong coupling tests of S-duality.
Yes.
So that's S-duality of n equals 4 superangular theory.
I spoke to Kumran on this podcast. I'll place a link on screen and in the description as well.
Right. So I should admit that, so it was 1994. I was just out of my, I just finished basically my undergraduate studies. I finished the military boot camp, and I just went to Europe. And I was going to graduate school late this year. It was a very hot summer. And at Witten's talk on Seiberg-Witten theory, I fell asleep. So it was, I
remember. I wasn't there, but I remember you telling the story.
Yes, I was asleep, but I must be ashamed. I am ashamed. I could not really comprehend the significance of what was going on, but I was impressed with the formula he wrote for certain quantity, which is called prepotential of theory. So, just to recall, Seiberg-Witten solution was the ansatz, or rather, for what is called low energy effective action of some gauge theory. They said that the quantity which they wanted to compute, the one which determines this low energy physics, can be expanded in power series in instantons. So what are the instantons? So this gauge theory, being non-abelian gauge theory, the there are configurations of gauge fields in one could say in the vacuum, where they fluctuate in a way which changes the topology of the gauge bundle on which they are defined. So let me maybe unpack that. The thing which is not often appreciated is that the fact that our world is described by gauge fields means that, maybe conceptually or maybe physically, there are extra dimensions to the world we live in. Because what these gauge fields are, they describe the transport of things over our space-time, but which happen in a
Yes.
kind of a additional space which is fibered over our space-time. And this space could be a group. So typically, one takes, as a basic object, one takes the principal bundle. So the fiber of this vibration is just a group manifold. Or it could be a space on which the group acts. So for example, fermions of the standard model, they are all sections of some bundles which are associated with some principal bundle. Now, one can take the totality of those fibers of a space-time and look at the space, the resulting total space. So it will be a manifold of dimensionality 4 plus the dimension of the group. So if the group is SU2, the total space will be 7-dimensional. If the group is SU3, the total space would be 12-dimensional, and so on. Some people like group E8, so the total space would be 252-dimensional. At any rate, just given the fact that your base space is your 4-dimensional space-time and the fiber is the standard group, doesn't specify uniquely what would be the total space. So there are different ways of fibering this group over the base manifold. So the ways to parameterize, to enumerate the topology of those total spaces is a subject of the study in I would say homotopic topology. And so there are special special classes which are responsible for those classifications, called characteristic classes, found by Podjagin and Chern. And so in doing gauge theory, we're actually doing a little bit of quantum gravity, in the sense that we are summing over different topologies of this total space. So when I say summing, I mean it in quantum mechanical sense. So if you think about Feynman path integral, which is the kind of integral over paths over possible trajectories of evolution of your system, in gauge theory, an evolution of the system involves the choice of a total space of a principal G bundle. And so we are summing over topologies of those bundles.
Let me see if I can break this down for the audience so far.
Yes.
Okay, and you tell me if I'm incorrect at any point. So space-time, we ordinarily think of it like X, Y, and Z. And then, well, there's also a time. So
yes.
You get X and Y, the plane that most people know about, by doing X cross Y. So that's something that people are familiar with. You take R, R1, and then you cross it to get R2. And then you're wondering, well, what is this fiber business that people are talking about? Locally, meaning if you look closely, you can think of a fiber as another cross. So we're just crossing with a gauge group.
So your example is already in your example. Yeah. We can give an example of a non-trivial bundle.
Sure.
So if your y variable is compact, it's actually not aligned by the circle. And now I'm adding x. Sorry, well, x was first. Let's say y was first.
Sure.
So I want to fiber the line over a circle. And so one way I can just take a direct product. So I will get the space which I will get will be a cylinder. I think I even have a cylinder drawn on my blackboard somewhere. But anyway, so it's a cylinder. We would call it it's a trivial bundle. So this is a cylinder. So the base is a circle and the fiber it's a line. But now let's there is another option, which is to say that as I go around the circle, my line flips orientation. And so it comes back as the same line, but it's inverted. So I used the action of the group Z2, the two-element group, which acts on the real line by multiplying x by my -1. So x goes to negative x. And so that gives you another space, which is known as Möbius strip, and that's a non-trivial bundle.
Right.
But you can also fiber the circle over a sphere in a non-trivial way. So let's take our two donuts. It's probably a good place to start. Now imagine, so I would think of so a donut is a product of a two-dimensional disk times a circle. So now what I want to do...
and these two donuts currently are disconnected.
Yeah, so they're separate, two separate donuts. Unfortunately, I don't have donuts with me.
Tim Hortons is what they would say here in Toronto.
Right. Yes. Also coffee. And now I want to take the boundary of those donuts, of those two donuts. So those would be products of S1 times S1. So now I want to identify the first S1, so they will be the same S1. I glue them together. But the second S1, the fiber, I want to identify with a twist. So I can, in such a way that as I go around the first S1, the second one makes the full rotation. It's almost like this example with the Möbius strip, but now the rotation is 360 degrees, and it's a rotation of a circle, not the flip of a line. So if you make a little mental exercise, glue these things together, you will realize that the resulting space is now a three-dimensional sphere. So one way to maybe imagine this is to actually embed take one donut and then realize that the complement to this donut in a three-dimensional space is actually topologically also a donut if you add a point at infinity. And so the union of those two donuts is the complete three-dimensional space with a point at infinity, which is a three-dimensional sphere. And it turns out that if you are studying the parallel transport on this bundle with non-trivial topological class, the minimal Yang-Mills energy configuration will be not flat, so the curvature will be non-zero, but it will have a very interesting property. It will be self-dual or anti-self-dual. So this is something which is specific to 4 dimensions. There is so if you list the coordinates of a 4-dimensional space-time, like x, y, z, and t, and suppose we orient them. So I say x, y, z, and t. And now, if you have a two-form, so two-form is something which likes to take in two planes or bivectors and produce numbers. So, for example, I take x, y. But if I remember, I had x, y, z, and t. So if I took x, y, then the remaining is z, t. And if I took x, z, the remaining would be y, t, and so on. So there is this duality between two forms, which is given by the orientation of the 4-dimensional space. And so the minimal energy configurations turned out to be such for which the curvature is self-dual. So if you apply duality to it in that sense, you get itself or maybe negative of that, depending on the sign of the topological class. So these are called instantons in the technical sense. But this is not the most general definition, of course, of what instanton is. And the significance of those solutions in quantum field theory is that these are configurations for which most of the action in both literal and mathematical sense happens in a kind of compact region of space-time. And here I should make a disclaimer that the space-time I'm talking about is not the real space-time. It's the Euclidean space-time. So,
which incidentally is real.
Which is incidentally real, but it's also imaginary. So in this real manifold, what we perceive as a time direction is actually imaginary.
Yes.
I don't like when people actually present it this way. I like to think of it as a part of the structure in which we study quantum fields on manifolds endowed with complex metrics in general. And so the metric can be real with different signature. So, square of the distance and time direction could be positive or negative, or it could be positive in all directions. So we call that Euclidean signature metric. But in general, we could and it should also study the metrics which are just complex. So the matrix elements are complex. The values of the metric are complex. And but that's maybe a slight digression. I'm sorry, this is a bit technical.
That's fine.
Anyway, so Seiberg and Witten wrote a formula, and they said that to really understand this formula from the first principles, one should derive it by doing honest path integral in supersymmetric gauge theory and evaluating those contributions to the effective action coming from those peculiar fluctuations of gauge fields, which happen in compact regions of space-time, of Euclidean space-time.
And the moduli space of instantons, is that a connected space?
So it is connected for each topological class. So if you fix the topological charge, it is connected. Mm-hmm. But for different topological charges, they are disconnected, distinct spaces. Mm-hmm. So a priori, mathematically, you would have said, okay, I mean, I have just an infinite number of integrals to compute. Why would they combine into something nice? So I would say that you never approach an interesting problem directly. It's very hard to to study things face on. You need some kind of preparation work, and maybe if you're lucky, you will get to the point when you can actually hit on the problem you're actually interested in, or you dare to be interested in. So
at this point, you were exploring, hoping that you were going to get to the solution, but allowing yourself to not get to the solution because it was interesting what you were exploring anyhow?
Right. So the goal was, at this point, I mean, I had to familiarize myself with instantons, with modular spaces of instantons, what they are, what they look like, what do people know about them. And so one thing which became popular at the time was the study of quiver varieties, but they were not defined as the modular spaces of solutions of some partial differential equations. Waffen and Witten mapped this property to the very non-trivial property of the four-dimensional gauge theory, which inverts the gauge coupling. So somehow they related the coupling of gauge theory to the geometry of some, at the time, abstract two-dimensional torus elliptic curve. So that was part of one of the hints towards the BPS-CFT correspondence. That some structures found in the studies of four-dimensional gauge theory, structures involving supersymmetry and the cohomology of some supercharges, are related to the structures found in two-dimensional conformal field theory.
Right. So just to linger on this point, so many people have heard of ADS-CFT, and that involves differential geometry and harmonic analysis and string worldsheets and so on. But there's also something else called BPS-CFT, which you helped popularize and articulate.
Well, BPS-CFT was just maybe a joke term which I coined at the time because it sounded like ADS-CFT. But of course, it's it's just as ADS-CFT is a kind of a string duality. It's a kind of open-closed string duality in my mind. even though some people claim it's just holography in its purest form and doesn't require string theory, I don't think it's the case. I think it's...
Oh, you think it's string dependent? It's not just string inspired?
I mean, it's it's one of these things which makes string theory great, I would say. That it allows you to... it gives you a mechanism. It gives you a mechanism for holographic duality. And, ADS-CFT in that sense is a projection of some 10-dimensional entity. So, or 11, there are versions of ADS-CFT which use M theory. So it turned out that the integrals which one had to compute to get the Seiberg-Witten solution were independent of that parameter. So you can hope that if you send it to 0, you get the same answer as if you don't. So this is one of the tricks which I learned essentially from Witten. Witten used in his studies of supersymmetry breaking a quantity which is now called Witten index, which is the also a partition function. It's a kind of a partition function of a quantum system with supersymmetry, which differs from the conventional partition function where you average exponential negative Hamiltonian divided by temperature. You also insert the operator which weighs bosonic and fermionic states in your Hilbert space with different signs. And so Witten showed that in many favorable circumstances, this partition function is independent of the temperature. And so you can compute it in different limits when temperature goes to 0 or temperature goes to infinity. And when temperature goes to 0, this partition function receives contributions from ground states only,
right?
So from the vacuum. And when the temperature goes to infinity, it is usually the regime where things are computable. And so one of the consequences of this method is the physics proof of Atiyah-Singer index theorem, which was used, for example, by Luis Alvarez-Gomez, my current director. So physicists like to, if they can prove that there is a parameter in your Hamiltonian or in your action or in your system to which the observable you want to compute is insensitive, then you vary this parameter as much as you can and try to find a regime in which things become computable. And so in my story, one of these parameters was this parameter of non-commutativity.
Right.
Unfortunately, so this trick cured one half of the problem, namely it dealt with this singularity of the modular space of instantons, which corresponds to small distances in space-time, so things which happen at short distances. But since I'm interested in working over R4, so we want to understand physics on the four-dimensional flat space, unlike mathematicians who use instanton modular spaces for things like invariance of four manifolds, which is the content of Donaldson theory, for them, the interesting spaces are compact spaces, even though sometimes with very clever tricks, they draw conclusions even for R4 and famously found that there are, unlike all other dimensions, so as a smooth manifold, there is only one R1, there is only one R2, only one R3, only one R5, only one R6. There is only one Rn for any n except 4. And 4 dimensions, there are exotic Euclidean spaces, which is quite contrivial.
Just a moment. Do you think that fact is connected to the R4 of our space? The fact that our space-time is R4?
Could be. Yeah, because it has to do with the fact that two-dimensional surfaces meet in 4 dimensions and they don't meet in higher dimensions generically. And so the fact that certain things meet often, like probabilistically. So if you throw random walkers, it's probably crucial for life. So let me just put it this way.
Okay.
I mean, life needs interaction and propagation.
So the exotic R4 is our world. The R4 is our world because there's an exotic R4, and if there wasn't, then we wouldn't have enough interactions for us to be here?
Right. So, I would say, I don't know what the causality is, but I would say that the reason exotic R4 exists is probably important in things like having chemistry and things like that. So there is certain topology involved, in having complex structures, in having biochemistry, depends on certain topological features of our space and space-time. And some of these things are crucial in having in the construction of exotic R4. So these things might not be unrelated, but since it's discussing things for which you have only one sample, it's hard to draw conclusions.
Because I haven't heard anyone connect chemistry to R4's exotic property. Unless this is just a speculation of yours, you're not sure.
No, well, we could probably elaborate, but I mean, I'm not strong in chemistry, so I probably, if I venture in this direction, I'll probably say something silly. But just I would say that the fact that four-dimensionality of, well, okay, what do we know? We know that 4 dimensions are special in having interacting, propagating vector fields. So gauge theory as quantum theory is well defined in 4 dimensions and has very interesting properties, which is and so it is not well defined in 5 or higher dimensions, and it's less interesting in fewer dimensions. People study it in 3 dimensions because it still has some qualitative features, but it's there are certain things you get almost for free because you get mass scale for free and so on. In 4 dimensions, things happen just, they're kind of on the boundary between things becoming trivial or ugly. So it's 4 dimensions is an interesting border case. And the fact that the possibility of exotic smooth structures in 4 dimensions uses the same kind of coincidences, which is all I'm trying to say about that.
Okay, so getting back to the story.
So back to the story. So in physics, I'm interested. So in physics, I need to, for physics applications, I need to compute meaningful integrals over the modular space of instantons on literally non-compact infinite R4. And this modular space is again non-compact because now those instantons, which are like pseudo particles, like they're like events in space-time, they can run away to infinity. So you can have a sequence of events which happen here and then on Saturn and then on in Andromeda and then go all the way to infinity. So there's no limit to that. So again, I'm in trouble because I cannot integrate by parts. I cannot. I'm not sure my integral is convergent. Life is difficult, so I need to invent another trick to somehow cure that possible divergence or non-compactness at least. Now, if we are doing something on R4 has a beautiful symmetry. It's a symmetry of rotation. Well, it has also symmetry of translations, but translations act without fixed points. So it will, if we use translations, it will kill everything. So it's not the right symmetry in this case. The right symmetry to use is to use the symmetry of rotations. And so the group of rotations of Euclidean 4-dimensional space is the group SO4, and its maximal torus, maximal abelian subalgebra subgroup is 2-dimensional, and it's generated by rotations in 2 orthogonal planes. Now, of course, if you just do some mathematical construction, which is completely artificial, first of all, you might make mistakes, but also you lack intuition. So it would be hard to know what is the right way to proceed. What are you doing?
Meaning you lack physical intuition?
Right. So this mathematical construction was nice, but I wanted to have some kind of physical understanding where these parameters come from and what would be the physical realization. Is there a physical meaning for such a deformation? Remember this. I was doing this in the late 90s, and at that time, even though the non-commutative field theories were already popular, and non-commutative deformation breaks Lorentz symmetry, because you see, if I tell you that x and y don't commute, the fact that x and y commute in one way and z and t commute in another way breaks the symmetry between x, y, and z, which is part of the Lorentz symmetry. So people started discussing quantum field theories which were not Poincare invariant, but people were reluctant. So this partition function scaled like a partition function of a non-ideal gas, where the role of the volume of the space in which the gas was confined was played by the inverse product of these parameters epsilon 1, epsilon 2. And the leading term, the free energy, so it's the free energy per unit volume, was the Seiberg-Witten prepotential. So first I discovered that experimentally, just by expanding it term by term, because I felt like these partition functions were good for something because they were so beautiful. They fit nicely to each other, one instanton, two instanton, so on. And then when I saw that the one case people computed, the one instanton per term people computed, and sometimes two instanton terms people computed by very hard work, matched with what I got by relatively simple work, then I was convinced it must work. But of course I was not very confident in myself, so I had to go up to 5 instantons and get some help from numerics, and got some errors along the way, so I had to.
Is that the one about the story where you were working for 2 weeks on a laptop and then you were in a hotel room and it worked out? That's a different one.
That's a different story.
Okay.
That's a different story. But by that time I was much more confident.
Okay.
So that's when I published it. I made a conjecture in this paper that this partition function, which was a deformation it gave more than Seiberg-Witten prepotential. It gave something else because it had two more parameters, and so the conjecture was that it gives the amplitudes of topological string, and the reason for that we can discuss, and also that it is given by some conformal field theory, or some deformation of conformal field theory. So that the structure which I saw in this partition function was that of some two-dimensional CFT hiding in the supersymmetric computation in 4 dimensions. So that's that. It was the moment both of joy and frustration, because it felt like I should be able to prove it, that it's not just conjecture, but just to prove that indeed the curves that Seiberg and Witten proposed and conjectured, and people then extend their conjectures to other gauge groups and types of theories with various metric content, should be provable, but I was too close, and it was kind of, I couldn't do it. So it was, it took me another year and another happy meeting, just fortunate meeting with the right person at the right time to be able to prove at least some of these conjectures.
Mm-hmm.
So that was the meeting with Andrei Okounkov, just on the train station in France, in Bure-sur-Yvette. And so I knew Andrei from before, but we basically just played volleyball together. When I was in Princeton as a student, he was at Princeton as a postdoc, and we just played volleyball, but we never really discussed physics or math. I knew that he was an expert in combinatorics, and maybe he knew something about partitions. And so I just stumbled upon him on the train station, and he said, "What are you doing?" I said, "Well, I have this difficult problem when I have a sum over infinite set of partitions, which I believe has this hidden structure there with curves emerging, but I don't know how to prove it. I mean, I don't have. It feels like it should be should have something to do with conformal field theory in two dimensions, but I'm not sure exactly what." And he said, "Well, but you are in luck because I'm computing the partition sums from dusk till dawn, and then from dawn till dusk." And he also knew of a problem about random partitions for which the answer is given by some kind of a curve. So he knew about some emergent geometry in the problem involving random partitions. And that was the famous limit shape of Vershik, Kerov, and Logat-Shep, which mathematicians studied for completely, different reasons, also in late 70s. And it was a different crowd of mathematicians interested in different problems. And but fortunately, I met Andrei, and he said, "Well, but this is a similar problem, so maybe there is a similar solution." And again, it turned out that the problem which mathematicians solved was for the trivial case, but with some ingenuity and Andrei had a lot of ingenuity at the time with this. So he used a lot of interesting complex analysis ideas to transform the problem of computing asymptotics to the problem of finding a limit shape. Limit shape is a kind of the most probable geometric shape in the ensemble of random geometries you are given. We found that indeed it was the family of Seiberg-Witten curves that governed the asymptotics of my partition function.
Wonderful. So you and volleyball.
Yes.
Because you went to Paris for volleyball and you weren't doing much math there, but then I think in 98 or so, you with Maxim Kontsevich, I think you went there for volleyball, but then it ended up being a fortuitous lunch, something like that, if I recall. You don't need to get into that story, but it's
volleyball is important for mathematicians for some reason. So I'm real amateur in volleyball. I sometimes I manage to get a good serve, sometimes I don't. But at IHS, which I visited in '98 and where I worked later for many years, there was this tradition that in the summer, in the compound where visitors live, people would play volleyball. And it used to be, the main driving force behind that used to be Professor Kirillov, Alexander Kirillov, so the inventor of geometric quantization, who was the advisor of Andrei Okounkov. And so that's why we played volleyball, because Kirillov invited us to play volleyball. And later, Maxim Kontsevich became the volleyball guru. And so every year in Bure-sur-Yvette, people play volleyball because Maxim is the driving force.
Okay, so from Moscow to Princeton to Paris to New York, you've worked in these different cultures. Would you say that the culture of academia is different there, or at least the one that you interacted with? Or would you say there's more similarities than dissimilarities?
Yeah, it's actually, I wouldn't say, I don't think they're so different. I wouldn't right now. After having spent 30 years in physics and math in between, I think it's pretty much universal. So I think that's what makes science beautiful. It's kind of universal. It's independent of the nationality and the.
Yes.
In Moscow, I had kind of I led maybe a double life, maybe triple life. I had two advisors who, one was my advisor in particle physics. Another was my advisor in, I guess, singularity theory. Both of them knew that I'm doing something else. I had some. My main interest was in string theory, in kind of modern mathematical physics, but part of the kind of training, maybe part of the coming of age kind of thing, you have to work on traditional problems for a while. So I was computing, radiative corrections to standard model parameters to get bounds on the mass of top quark. It was before top quark was discovered. So that was part of my work, kind of part of a duty, so to speak. So I worked with my advisor was Lev Okun, who was basically a phenomenologist, an expert in weak interactions. He wrote several very good textbooks on electroweak theory, on physics of elementary particles. But apart from one paper which I wrote with him on those bounds, we didn't work much. But he kind of protected me from, I guess he was my protector in many respects. We could get into that. Life in Moscow, so it was Soviet Union, just post-Soviet Union. It was very different from what it is now. So the expectations of young physicists and were different, and there were different obstacles and different challenges. My math advisor was Vladimir Arnold. He didn't know. I was just going to his lectures in Moscow State University, even though I studied at a different university, and he didn't know I was not a student there. So I just attended his seminar, his lectures, and he gave every year he would give a list of problems to the participants of his seminar, and if you wanted, you could work on them. And so I worked on one of these problems, and it was very useful for me because I learned about topology, about many things. But he actually gave me some advice, which I guess I used. And he gave me lots of advices, but one of them was to, always find all the parameters in your problem and always try to take them to extremes. That's the advice which you can take outside the science as well.
So your physics supervisor was David Gross?
In Princeton, yes. When I got to Princeton, my advisor was David Gross. But again, when I was a graduate student, David was kind of going through a complicated phase in his personal life, and he basically let me do whatever I wanted, which was the best case scenario for a good student. Good students should not ask problems from the advisors. They should find problems, and maybe if they have some difficulty in solving them, they should come to the advisor and ask for advice. So David gave me, when I was a student, he gave me some practical advices, but we started working together already later when I already had a job, actually. So, which was actually the best time, because I got to work with happy and confident David. So he already was in Santa Barbara, and I got him interested in non-commutative geometry. So we found interesting solutions of gauge theory non-commutative space. We found non-commutative monopoles and found that they actually carry the physical string attached to them. So the Dirac string of magnetic monopole of Dirac, the string of Dirac monopole, which is kind of imaginary object, on a non-commutative space becomes physical. And so these are sometimes called Gross-Nekrasov strings.
Right. So what's something else David Gross taught you about physics that wasn't in any textbook, something that you still carry with you today?
he always told me to believe in myself and to be confident, and that don't get intimidated by other intimidating people. So if people tell you that you should not work on something because it's wrong, or because it's morally wrong, or because it's whatever reasons, if you feel that it's important, work on that. So
Was there something in particular that you were insecure about, that you were coming to him saying, I'm not sure if I should work on this, and then it was that moment that he gave you that advice?
Well, it was I think it was before one of the string conferences. Incidentally, it was I think it was a string conference in Paris, and I think I was competing with the competing, kind of working on similar topics with the group of prominent physicists, and
so you felt in competition with them, like you felt there was a rivalry?
Yeah. So I was doubting whether I should maybe I should change the topic of my presentation at Strings and speak about something else. And because their paper didn't come out, my paper didn't come out, so we didn't know exactly what was who had what. And David told me that don't worry, just play it, keep your poker face. He had some stories when he was coming to a conference and somebody gave a talk saying that maybe it was Lenny Susskind, so David and Lenny had some kind of rivalry, saying that probably it was about instantons. So instantons are irrelevant in some problem, or irrelevant, I don't remember exactly. And he had the result which he could confirm with the models and examples, which showed precisely the opposite. And so it was a very happy coincidence. So it made a good show in the sense that people make strong claims, and then one claim after another, and then there's some discussion, and of course David was right. So in his story, so he told me that you should just aim for be yourself, believe in yourself, and present what you have, and maybe the other party doesn't have as strong a result as you think. And he was right. So it was the right thing to do.
So I've had another one of your collaborators on, Edward Frankel, and yes. I'll post that podcast on screen and in the description. He was on several times, actually, and he's coming up again to talk about the geometric Langlands. So what is it about Edward Frankel that you admire? You all both seem to get along, well, mathematically, but also as people, so you can speak about both.
Well, we are... what I admire about Edward, so he's, first of all, he's charming. He's very intelligent, very knowledgeable, but also... well, I would say that for a person of his charm, he's actually, has a big heart, which is very rare. So sometimes people kind of use the charm to their advantage, and eventually they become cynical. Edward is the opposite. So he's evolving, he's learning, and he's interested. He's interested in things I'm interested in, and so it's always I always learn something from him, and it's always not just a pleasure, it's a challenge and a pleasure to be in communication with him.
So mathematically now, what is it that you admire? So you admire his heart, sure, at a personal level?
Yeah, so he combines kind of a deep knowledge and understanding of very abstract things, but he also knows how to connect them to things which kind of I understand as a physicist. So he can speak to me both as a physicist and as a mathematician. So, and to some extent.
Yes. Okay. So earlier you also mentioned physical intuition, and I want to touch on this because while physical intuition can take you so far, do you find that it hinders at some point? Do you find that, well, it helps in general? And if it depends, then what does it depend on?
Well, on my path, I was not always guided by physical intuition. So either I would say I'm guided either by mathematical intuition or by physical intuition. So there is always some sense of beauty in both worlds, and they sometimes complement each other. Sometimes they're compatible. Well, there are, of course, historical famous examples where they are in contradiction, and then mathematical intuition, for example, for Dirac, was more important than physical intuition, and it led to a change in our physical understanding, like with the concept of antiparticles, with the positron, and things like that. But of course, physical intuition sometimes could be misleading because we are limited by our experience and the models we study. So again, the good example would be the invention of quantum mechanics. You have to really step out of your mind box to embrace the quantum intuition. You cannot understand it using everyday experience, and we get used to it. But to truly understand quantum mechanics, I don't know what kind of meditation you need for that. So I haven't found it. So I have a very good friend, film director Ilya Khrzhanovsky, who wanted to make sort of a quantum film, where you could kind of experience quantum reality through multitude of universes you live in. But well, I don't know. It's some people say that he succeeded to some extent. Some people say he made a step. But so we keep talking about this with him, whether maybe animation could be good media for kind of explaining what quantum world is, or.
So here's a question. I was just at dinner last night with some people, and it's commonly said that when we measure, we observe something real, and we don't see a superposition, and in part that's the measurement problem. And then I just asked, well, what would it look like if you observed a superposition? And the people were pausing it, because it's not exactly that you see something here and here, but it's half transparent.
No, we observe effects of a superposition because I think the issue is that the devices we measure with are kind of classical devices. So, and the way the brain we analyze this is a classical brain. Mm-hmm. So to really understand superposition as a quantum, you have to be a quantum entity to measure superposition.
So Greg Moore, which I want to talk about as well, he described something called physical math, and that's in contrast with mathematical physics. Now, I know that you didn't come up with that distinction, but do you see yourself as more of a physical mathematician or a more mathematical physicist?
I think of myself more of, so I'm more physicist than a mathematician, let me put it this way. So just that. But I'm equally interested in mathematics as I'm interested in physics. And for me, mathematical beauty is as important as physical beauty. Physics beauty, not physical beauty. Physics beauty. Physical beauty is also important, but it's a different.
Yes. Okay. Well, okay. Let's talk about mathematical beauty. Physical beauty is something for another time. But give a taste for what it is to to find something mathematically beautiful for people who haven't experienced that?
Well, of course, there are kind of professionals who come up with examples of mathematical constructions for laymen, which are kind of beautiful. For me, mathematical beauty is what unites distinct parts of mathematics. For example, the fact that you can think of prime numbers, prime integers, as of points on some space. So for me, this is a beautiful concept.
In what sense?
Well, it's in the sense that integers, they are analogous to the ring of polynomials. So the ring of integers, integers you can add, you can multiply, you cannot always divide, but some integers are divisible by other integers. So just like polynomials, you can add, you can multiply them. Some polynomials are divisible by other polynomials. So if a polynomial vanishes at a point, then it is divisible. Let's say polynomial of x vanishes at point A, it means that it's divisible by x minus A. So in that sense, prime numbers is what the other integers might be divisible by. So these are the analogs of those minimal polynomials, x minus A. And so you can develop some kind of geometric intuition about integers starting from that observation.
Okay. You have a lecture titled Natural Language, Geometry, and Physics.
Yes.
What I want to know is what's the relationship between human language and then the mathematical language that is used to describe the universe?
I'm very much impressed and I'm amazed by the fact that human language, so natural language in the human sense, evolves. So it's not a static object. It's a kind of a dynamical system, and as such, I was proposing to study it as a physical system, like a growing crystal or melting crystal. So in my work on instantons, which I reviewed for you, the concept of emergent geometry appears. So the problem from gauge theory became a problem of enumerating some combinatorial structures, partitions, which you can visualize as Young diagrams, or you can visualize as some kind of paths with the wiggles,
right?
Wiggly paths. And the enumeration of those objects, you can also view as a search for what's it called, equilibrium distribution in the ensemble of dynamically changing shapes. So from one Young diagram, you can go to another one by changing a few wiggles. And so you can assign certain probability for those wiggles, for wiggles appearing or disappearing. So some kind of transition probabilities or transition amplitudes. And you can ask, what if those wiggles were analogous to the words or the sentences in the natural language? And so the way the language changes in time could be maybe assigned some transition amplitudes, transition probabilities, and maybe there is some emergent geometry which emerges as the most probable configuration. So maybe the natural language, to the natural language, certain geometric shape is associated, just like to these random partitions in my instanton calculus. The Seiberg-Witten curve, the geometric object was associated. So language is much more complicated than the ensemble of Young diagrams. So the geometric shape which is associated with language probably is more complicated than the two-dimensional surface, but maybe it's less complicated than the world itself. So, so I was proposing in this lecture to embark on the statistical analysis of the language, not in the way it's done in the large language models, but in doing some kind of time sequence analysis of language. So to study how it changes from century to century.
Interesting.
Maybe from year to year. But also, the pun in this title was that the geometry is the language of nature, of physics. So that's when there's a natural language in that sense.
Yes.
But also physics is. So
have you followed up this work?
Not quite. Not yet. So,
but in the back of your mind, are you developing conjectures, or you've just abandoned it and it was a fun activity at the time?
No. I'm as I told you. I mean, this is a very hard problem. So you don't attack it head on. So I'm developing models which will kind of surround this problem, and then I will attack when the time comes. So I'm developing other models for simpler systems, simpler than languages.
So speaking of Young diagrams, and I don't want to get us into more ground that'll take us quite some time to get to, but there is gauge origami. And if I understand that correctly, that has to do with counting Young diagram configurations associated with tetrahedra, whose edges are colored by vector spaces.
So, so we should fast forward to a few years later. So,
okay.
So 2003, with Andrei Okounkov, we understood how to evaluate asymptotics of the partition function, but then it was understood that the whole partition function is a very meaningful and interesting object, because it contains information about strings, black holes, local Calabi-Yau's. Also thinking about this partition function, people came up with the notion of the so-called refined topological string. So this whole thing was worth studying. And so one way to approach this problem is to say maybe the Seiberg-Witten curve, which is the object which captures the limit shape, the asymptotics of the partition function, can be somehow quantized or deformed, and it had to be deformed by two parameters, by two deformations, to capture the structure of the whole partition function. So this led to the notion of QQ characters, which is maybe not the most fortunate name, but well, it has a reason. I mean, this name didn't come from nowhere. So it's a notion. It's certainly observable. So it's a way to measure the partitions. So it's a device, like if you like, it's a device with expectation value. First of all, contains information about the shapes of the random Young diagrams and so on, but on the other hand, has some analytic properties allowing to maybe compute it or to write some differential equation on it. So I realized that one can define some kind of gauge theory problem. It's best done in the context of non-commutative gauge theory, where gauge fields live on a tricky space-time, which has different parts. So it's four-dimensional, but it's not like four smooth dimensions. It's four dimensions with coordinates x, y, z, t, and then four dimensions with coordinates, I don't know, u, v, w, s.
Sure.
Okay. So then, once I understood that it works and it has good it has good properties, and it actually is behind this observable, which I call Q character, for the reason which maybe I will explain later. I ask myself, this is where the mathematical intuition steps kicks in. So if you have two transverse 4 planes inside the 8-dimensional space, why not adding other 4-dimensional planes? And so the total number of 4-dimensional planes you can have is 6, and so you can label they would be in correspondence with the edges of a tetrahedron, and the axis of the 4 complex dimensional space would be in correspondence either with vertices or with the faces of a tetrahedron, depending on how you want to think about it. So the tetrahedron is just an object which helps in just keeping track of all the moving parts of this construction. But it's really just it's a gauge theory which lives on a particular singular spacetime. And the reason it's interesting to study is because from the point of view of the observer who lives on just on only one of 6 sheets of this complicated structure, you're just exploring all possible local or semi-local observables of gauge theories. You have observables inserted at a point, you have observables which are inserted along a 2-dimensional plane or another 2-dimensional plane. And it's constrained to be 6 because of the rotational symmetry. Of course, if you don't have any symmetry in question, you can, of course, place things any way you like. It will be kind of unruly. But if you insist on things being invariant under rotations in now 10-dimensional spacetime, you will be bound by placing things at along the coordinate planes. And so this is what this gauge origami picture is emerging. It's called gauge origami because it looks like you're folding paper at different folds.
Yeah, right. Is this at all related to the positive geometries of NEMA or the amplituhedron?
Not as far as I know. But in my experience, things are rather related than unrelated. So whenever somebody claims that here I come, at least in my experience, every time a person comes up and says that here I have a construction which deals with the same objects, but it has nothing to do with the work of Nikita, I later prove him wrong.
Okay. What's something that you've learned as a lesson from collaborating with Edward Witten? And also, I'd like to get to Greg Moore as well, but afterward.
So, I guess with Edward, I share kind of affinity to rigor. And he told me on many occasions that this desire to be rigorous is sometimes is very constraining. So sometimes it really stops you from doing something because you cannot proceed in a rigorous manner. But I found that one can be rigorous in different field, in a kind of so our stumbling blocks were kind of complementing each other. And so whenever we were trying to in our work we were trying to combine something I learned with something he learned. So he was working with Kapustin on gauge theory approach to geometric Langlands. I was working on my partition functions. I was certain it was the same thing. So these were very similar. I mean, the domain, the realm where we were discussing the subject of our study is the same subject, and somehow So it was certain that there was a way to relate our viewpoints. But I had my stumbling blocks and he had his stumbling blocks, and it just turned out that somehow they were at the right places, and so I could advance where he couldn't, and he could advance where I couldn't. And so I guess the main lesson from Edward, which unfortunately I could still to this day I cannot quite embrace, is that one should work on some problem and then move on, and then maybe come back to it. I seem to get stuck on things for a much longer time than he does. So he manages to learn about many things and to advance many things and to be useful in many things because he doesn't get stuck in the problem.
And by getting stuck in the problem, you mean that if you're not making progress, you still continue to think about it. Whereas with Edward, he will transition?
Probably, yes. And I mean, it's not that I'm continuing to think about the problem, not because I'm kind of stupid, that I don't understand that it's at least nowhere. It's because I feel like there is a progress to be made, or I just cannot not do this. It's one of these things when you do what you cannot not to do.
Like it's an obsession?
Like an obsession, yes. Like an obsession.
Okay, so what did you learn from Greg Moore?
Persevere. So if you persevere...
The opposite. Okay, got it.
So Greg is close to me in that sense, yes. You can get obsessed with things and it's okay.
Yeah. Do you have a specific example in mind? With you working together with him?
Yes, we had so remember I told you that before attacking Seiberg-Witten problem, one had to learn how to compute certain integrals. And so we were playing with integrals over like hyperkähler manifolds, hyperkähler quotients, using all kinds of equivariant localization, all kinds of tricks. And at some point, so this was my what's this called? Miraculous year. So this 1998, when I met Albert Schwartz in Santa Barbara. Also in Santa Barbara, I met at some point Greg Moore and Saf Seti. I don't know if you know Saf Seti. He's a professor at Chicago. So Saf was presenting his work with Curt, I think, on the computation of Witten index for the quantum mechanics of D0 branes. So D0 branes are the interesting particles which are defined as D branes. So they are particles in type 2A string theory. But secretly, the secret life is that they are also black holes and also gravitons of 11-dimensional supergravity. And if so, the main conjecture of Witten of 1995 was that the strong coupling limit of type 2A string theory is 11-dimensional M theory, which contains 11-dimensional supergravity in its low energy limit. And for this conjecture to be consistent, D0 branes should form bound states. So you should have a bound state with certain properties for every number of D0 branes. And so it's a question about supersymmetric quantum mechanics. This is a question about conventional mathematical physics, I should say. And so Saf was discussing the case of two D0 branes, so just two particles. And he showed that to compute Witten index, one had to compute certain integral over matrices, supersymmetric matrices. And Greg and we were in the audience, and I remember after this talk, I told Greg that this is an example it's one of the examples of the integrals we should be able to compute, because this is the space he's integrating over happens to be, among other things, also a hyperkähler space. And so we quickly set out to do the calculation using our tricks. And I quickly confirmed that for 2 particles, it produced the answer that Saf was giving. But for 3 particles, it was already a kind of complicated multiple residue thing, so it looked hopeless. But Greg, with his perseverance, he set out, I don't know how many hours he spent, but he carefully analyzed all these residues, and it came out to give the answer which we wanted. So then, of course, once you know it works, then you can be clever about it and find more scientific ways of proving what you want to prove. But you really need this confirmation, and so this was just one example of what Greg, with his ability to do tour de force calculations, persevered and pushed us. And so we were able to prove the conjecture of Michael Green and Godperly, which in the thanks to the work of Satie and Stern, actually implies the fact that for any number of de Sitter branes, they form a bound state. So in that way, we saved M theory.
Hi, everyone. Hope you're enjoying today's episode. If you're hungry for deeper dives into physics, AI, consciousness, philosophy, along with my personal reflections, you'll find it all on my Substack. Subscribers get first access to new episodes, new posts as well, behind-the-scenes insights, and the chance to be a part of a thriving community of like-minded pilgrimers. By joining, you'll directly be supporting my work and helping keep these conversations at the cutting edge. So click the link on screen here, hit subscribe, and let's keep pushing the boundaries of knowledge together. Thank you and enjoy the show. Just so you know, if you're listening, it's CurtJaimungal.org, CurtJaimungal.org. What do you want to be known for?
Oh.
Other than saving M theory.
No, I would like to this is so I'm pushing my physics hat. I'd like to contrast some of my calculations, some of my predictions with the actual experiment. And so right now it seems that the most promising venue for high energy physicists to make testable predictions is condensed matter physics.
Right.
So with my current student Yugov, we just published a paper where we applied a clever mathematical technique from mathematical Young-Mills theory to the physics of two-dimensional graphene. So maybe when people finally discover superconductivity, high TC superconductivity in graphene, maybe they will use some of our constructions. So I would be happy to be known for that.
Now, speaking of your student, what advice do you have for researchers, young and old?
Be passionate about what you do. I mean, that's the best advice. Many years ago, like 20 something years ago, I gave an interview to my former university, to my undergraduate school, and so they asked me, what advice would you give to current students? And my advice at the time was, don't overburn. So don't burn yourself. So don't do too
burn
much.
Out. Yeah.
Don't burn out, right? But I think these days the attitude of modern students is different. So my advice is don't go the opposite. Don't go the opposite way. Be passionate about what you do.
Oh, okay.
Burn yourself, whatever you want. So just burn yourself.
So wait, are you suggesting that, I don't know how long ago that was, a decade or 2 decades ago?
2 decades ago.
Yeah, okay. Are you suggesting that back then the problem was over passion and it would be to their detriment? And you're saying now there's maybe some apathy?
Maybe people, well, I don't want to put it that negatively. I just want to. I think people now know a little bit better how to take care of themselves. Now, in my time, it was a really typical thing that people would commit suicide because they were not successful. I mean, not because they would overwork themselves, and I think people are now much more aware of those things, and maybe there is a little bit of apathy too.
So personally speaking, how do you stay strong during the bad times?
Well, I guess I was lucky not to be in too dark, times, but I do get stressed a lot, and physical exercise is one way to deal with it. So I exercise a lot and try to. So there are, lots of ways to take care of yourself, which are important. So breath work, meditation, yoga, gym, be in nature, bicycle, skydiving, see other people, travel, see the world, spend time with the native people, just all kinds of things.
Well, speaking of spending time, thank you for spending so much time with me.
You're welcome. It was a pleasure.
It's 3 hours at this point, over 3 hours now. I appreciate it. Thank you.
Thank you.
Hi there, Curt here. If you'd like more content from Theories of Everything and the very best listening experience, then be sure to check out my Substack at Jaimungal.org. Some of the top perks are that every week you get brand new episodes ahead of time. You also get bonus written content exclusively for our members. That's CurtJaimungal.org. You can also just search my name and the word Substack on Google. Since I started that Substack, it somehow already became number 2 in the science category. Now, Substack, for those who are unfamiliar, is like a newsletter, one that's beautifully formatted. There's zero spam. This is the best place to follow the content of this channel that isn't anywhere else. It's not on YouTube. It's not on Patreon. It's exclusive to the Substack. It's free. There are ways for you to support me on Substack if you want, and you'll get special bonuses if you do. Several people ask me, like, hey, Curt, you've spoken to so many people in the fields of theoretical physics, of philosophy, of consciousness. What are your thoughts, man? Well, while I remain impartial in interviews, this Substack is a way to peer into my present deliberations on these topics. And it's the perfect way to support me directly. CurtJaimungal.org or search Curt Jaimungal Substack on Google. Oh, and I've received several messages, emails, and comments from professors and researchers saying that they recommend Theories of Everything to their students. That's fantastic. If you're a professor or a lecturer or what have you, and there's a particular standout episode that students can benefit from, or your friends, please do share. And of course, a huge thank you to our advertising sponsor, The Economist. Visit economist.com/toe, TOE, to get a massive discount on their annual subscription. I subscribe to The Economist, and you'll love it as well. Toe is actually the only podcast that they currently partner with, so it's a huge honor for me, and for you, you're getting an exclusive discount. That's economist.com/toe, TOE. And finally, you should know this podcast is on iTunes, it's on Spotify, it's on all the audio platforms. All you have to do is type in Theories of Everything and you'll find it. I know my last name is complicated, so maybe you don't want to type in Jaimungal, but you can type in Theories of Everything and you'll find it. Personally, I gain from rewatching lectures and podcasts. I also read in the comment that TOE listeners also gain from replaying. So how about instead you re-listen on one of those platforms like iTunes, Spotify, Google Podcasts, whatever podcast catcher you use. I'm there with you. Thank you for listening.